It always takes a minute to load. Awesome. Well, thanks everyone today for joining us for virtual lab notes. This is, I think, the fifth or sixth session that we've done, and we're very excited to be here and to start this presentation. Please let me know in the chat if you're having any difficulty seeing my screen or hearing me, and I will help you as best as possible. My name's Corey. I'm the Director of Development in the College of Sciences at UNLV, and I'm very excited to have you all here and really excited for our topic. Just a couple reminders as we get started. Make sure your microphone is muted and you keep it muted throughout the presentation. Make sure that that camera button and the microphone button below you are red. Use the chat function if you're having any issues or you have questions. Feel free to ask questions throughout the presentation. I will keep track of them and ask them to Dr. Salamat at the end. And if you encounter any issues, you can bring them into the chat to me, or you can also check out this link right here, support.google.com/meet, and try to see if you can troubleshoot the issue on your own. We are recording this, and so it will be available within the next week at the link below on our virtual lab notes page. And just as a reminder too, if you hover over the primary image on your screen and click the little thumbtack button, that will pin the presentation so you can follow along as Dr. Salamat gives his lecture. And with that being said, I just want to let everyone know we will not be doing a virtual lab notes session for December. Our faculty will be earning a very well-deserved time off for the craziness that this semester has been. But we will resume in January 2021. Look forward to having you all. I will be sending out a short survey of this semester's for anyone who attended a virtual lab notes session this semester with any suggestions or tips that you might have for the next year and any topics that you would like to hear discussed. Thank you so much for your support. This has been a lot of fun, and it's been great to see our faculty showcased in the College of Sciences. And with that being said, I'm going to quickly introduce Dr. Ashkan Salamat, who is a professor here at UNLV. He's an assistant professor in the Department of Chemistry and Biochemistry, and also an adjunct professor in the Department of Physics and Astronomy. He received his master's in chemistry from Imperial College, United Kingdom in 2006, and he completed his PhD at University College London in 2010. He then spent 3 years in France at the European Synchrotron Radiation Facility, leading an independent research program exploring materials under extreme conditions using X-rays. Dr. Salamat then went on to be a postdoctoral fellow at Harvard University under the supervision of Professor I. Silvera, working on warm dense hydrogen and exotic quantum states of matter. Dr. Salamat leads a vibrant research group consisting of an assistant research professor, postdoctorate, 5 graduate students, and 3 undergraduate students. The research goals of Dr. Salamat and his research team are exploring the high energy density landscape of light elemental, or HCNO, systems and their related compounds, which are relevant for fundamental and applied sciences. Dr. Salamat is the recent recipient of the Early Career Award from the Department of Energy, exploring a new group of materials known as metal superhydrides, leading to the discovery of room temperature superconductivity. So without further ado, let me give you Dr. Ashkan Salamat to present the future of energy, exploring superconductivity at room temperature. Take it away.
Thank you, Corey, for the very kind introduction. Much to the disappointment of the chemistry department, I'm actually a faculty here in physics and adjunct in chemistry, but that being said, okay, so I'm very excited for this opportunity, mostly because my mother's on this call, and I'm very excited to convey to a general audience what we get up to as a group. I'm assuming you can see my screen and the face, right?
Yes, looks good.
Great. Okay, and so we've been involved in some very exciting science recently, and the idea here is to convey to a general audience the underlying quantum phenomena. These are some big scary words, but I'm hoping to dilute them down to a general audience level, and then to really highlight where we're going with this. It's a very new hot topic, and we're at the true cusp of this discovery, and the options for us are limitless. So I'm very excited to talk about this. Okay, so the theme here is room temperature superconductivity. I'm hoping by the end of this talk, you will appreciate what superconductivity entails and why it's so important at conditions like that of room temperature. Here at Nevada, we have a very strong group. In UNLV, we've named our center the Nevada Extreme Conditions Lab. And really, as the story unfolds, I'm trying to get you to appreciate the nuances of exploring the energy landscape and how we as extreme conditions scientists can utilize some remarkable parameters which Mother Nature herself can't really utilize and use. And we can exploit these and make materials that Mother Nature herself cannot make. And as a consequence, we end up making materials that have remarkable properties. So the two groups that have taken part in this are my group here at UNLV. This is a pre-COVID photo. Some of the players have left and graduated. We have new members that have joined. I'm very proud of my team. We have an exceptional team here at UNLV. The key player in all this, along with myself, is Dr. Keith Lawler, who runs the theory component of our group. And he and I have spent the last year hidden in our offices working on this project. This is the group of Ranga Diaz. He's at Rochester. This is a 2018 Halloween photo, I guess, that they timed really well for these times. But Ranga's in the middle. He is truly the pioneer of the electrical measurements for this and is really a world leader. And some of the measurements I'm going to show you are the first of their kind and truly cutting edge. So these are the two teams here at UNLV and here at U of R, upstate New York U of R. Sorry, someone just distracted me from the window. And so our discovery, this discovery, it was published recently. It made the front cover of Nature magazine, which is quite exciting, I guess. It made huge ripples within the media. So there was a serious amount of media frenzy. These are some of the bigger highlights that have come out of this work. Really, we had something like 95 different media outlets be in touch over the last couple of weeks. And the reason I'm showing this is because often in the sciences, especially in fundamental sciences, the work that we do is so removed from general audiences that it's very hard to get the general public excited about the fundamental esoteric work that we do. But the beauty of superconductivity and achieving it at a condition that's important for habitability of humans, can really resonate with the general public. And this is why this work is so exciting, not just from a pure fundamental point, which is it's remarkable, but the fact that it can make ripples, not only in terms of attracting attention from the general public, but actually contributing to a dramatic change in the way technology is used within society. So hopefully as the story unveils, you could appreciate why this work is so fascinating for such media outlets and why we really believe we can make a true difference to tomorrow. Okay, so I've used the word superconductivity like it's free, and here I'm going to try and convey the underlying principle here. This is a quantum phenomena. It's incredibly complex, but I'm just going to give you a slight flavor of it, a vanilla flavor of all this. And so in 1911, owners in Leiden, Amsterdam had just liquefied helium. He'd reached 4 Kelvin, so minus 263 degrees Celsius. And actually, he wasn't quite sure what to do with it. And what he did was actually start to measure the resistance, so the electronic properties of different metals. And what he found in mercury was a remarkable observation. He found that as he cooled down his material, this property called resistance, and I'm going to talk about it in depth, decreased and decreased like any metal that he'd seen. And at some dramatic temperature, or some critical temperature, pardon me, there was a dramatic drop to zero resistance. This was a remarkable observation. Prior to this measurement, it was still unknown what would happen to materials at very, very low temperatures. Following Onus's discovery, prior to Onus's discovery, there'd been a lot of speculation about what happens to materials as you cool them down. And so before the onset of quantum mechanics and a true understanding of the atomistic behavior of matter, there was a lot of speculation. Lord Kelvin, which the temperature scale was named after, the Kelvin scale, he had hypothesized that as you cool down materials, these things called electrons get frozen and you get an actual increase in this property called resistance. Dewar, who had recently liquefied hydrogen, had proposed a different alternative. And so there was a lot of contention regarding what happens to matter as you cool it down. Actually, at very cold temperatures, weird and wonderful and bizarre properties emerge. And so soon following the discovery of superconductivity by Onez, the Savoy Conference was set up. So this is the first meeting of the great minds of the world. You should all recognize Albert Einstein. And it turns out there was a memo, and 2 of the attendees did not get the memo. And the memo, I think, was you had to have a moustache to attend the conference. And neither James Jean or Mary Curie got the memo. And so with the exception of these 2, everyone else is busting a fine facial attire. So 1911, the Savoy Conference occurs. And actually, the main point of discussion at this conference was the observation by Onez. Onez had observed for the first time the onset of superconductivity, a unique quantum phenomena that until previously hadn't even been thought of. We didn't even have the tools to predict the onset of such behavior. And since 1911, there's been a huge amount of work done on the theory of superconductivity. There's been 4 distinct there's been 4 distinct Nobel Prizes in physics for superconductivity. Onez himself received one. Barden, Cooper, and Schaefer, who actually devised the first real underlying principle of superconductivity, also received it. In addition to this, there's been notable other members of the community that have received Nobel Prizes for just working on superconductivity. And actually, since its discovery in 1911 until now, there is no major consensus on how this property works. We have an idea for certain materials, conventional superconductors. We've even subcategorized these into type 1 and type 2, but the underlying principle is still not truly understood. It's just remarkable. And I'm sure there's plenty of other great minds that are going to contribute to the underlying principle of this quantum phenomena. So Onez discovers superconductivity. The great minds of the world meet up. They still don't understand it. We still don't understand it today, but I'm going to try and help you understand it just a little bit. So, in our daily lives, we normally interact with 2 types of solids. In terms of electronics, we interact with metals. These are prevalent in all types of technology and in hardware that we use. And we interact with another type of material, which we call insulators. These can be materials such as wood or such as plastics. And now, electronically, these 2 types of materials are distinctly different from each other. Metals, as we know from high school and stuff, these conduct electricity very well. And as you know, wood is not very good at conducting electricity. And so the distinct difference that drives how these materials behave is the way the electrons in the material behave themselves. The electrons are fundamental particles that make up all the matter in our observable universe. So in insulators, these electrons can be paired, so they see their friend nearest to them and they couple up. In metals, if you remember from high school, we talk about the sea of free electrons. These electrons are free in metals. Now, what happens when you run electricity through a material? So in a material, let's say, pick your favorite type of metal. We have the atoms that are here symbolized as cations. So let's say iron, for example. The reds are the iron atoms. And the atoms themselves are held together by basically a glue of electrons. And these electrons actually can move throughout a material. You can make electrons travel through a piece of metal. And the way you do this is you set up a potential difference. So you have a negative terminal and a positive terminal. And the electrons, which are negatively charged, see the positive terminal and proceed to walk towards the positive terminal. Now, on their procession towards the positive terminal, what actually occurs at conditions that are habitable to humans, so room temperature conditions, at room temperature, the atoms in materials actually start to move. So there's a thermal energy in these atoms, and these atoms are moving. And so as this electron is going from the negative terminal to the positive terminal, its path is not so smooth. It's constantly colliding with other atoms. It's actually colliding with other electrons. And as a consequence of this, sorry, I just jumped. And as a consequence of this, the electrons lose energy. So I have a piece of wire and I send some electricity through this wire. Because of how the electrons move in this wire, the amount of energy that I put at the start of the wire is not what I get at the end. And the main loss of that is heat. So actually, this internal resistance, in part, this motion, this wobble of atoms that stops the electrons from traveling through the material smoothly, results in a consequence of generating heat. And this heat leads to energy loss in the system. In fact, so I'm going to bust this video. If you run enough electricity, this is a steel nail. Here they're running a huge amount of electricity through the steel nail. If you drive enough current through any material, the force at which the electrons are moving collides so hard with the atoms that you generate a huge amount of heat. This heat can be so hot that just from applying electricity, you can melt metals. So in fact, metals are not that great for transporting electricity. And yet most of our grid, in fact, all of our grid, all of our electronics rely on this form of transportation. So if I run a huge amount of current through a material, I can heat it up significantly, so much so that I can melt the material. Now, what happens if I cool down the material? Well, if I cool down the material, those atoms that were moving before start to slow down and slow down. And as the atoms slow down, the overall resistance of the material actually drops with temperature. So if you take copper, which is the best conductor we have in terms of a metal, and you cool it down, the motion of the atoms in the copper slow down and slow down. As a consequence, the electrons can go from A to B much more smoothly, and that results in a lower measured resistance. Now, based on the discovery of Onnes, there is a special type of quantum material that becomes a superconductor. And so a superconductor behaves like any type of metal. So as you cool it down, its resistance lowers just like a metal, but at some critical temperature, the superconductor undergoes a transition into a unique quantum state where, as the consequence of this quantum state, the resistance of the material drops to zero. And now you have a material where there is no resistance. So just like previously, I showed the video where you run a current through a piece of metal and you can actually heat it up. In essence, for the perfect superconductor, you can pass as much current as you want through the material, and the material will never heat up. It loses no energy. There is no energy loss from A to B across a superconductor. This is remarkable. Zero resistance leads to zero power loss. And when I finish off the talk talking about the relevance of future technology, this is critical for us projecting how society can change as a consequence of discoveries like this. Okay, this is the hardest bit of my talk. Don't worry, there's plenty of more videos. So I'm going to try and explain to you what superconductivity is and how it kind of works in a very, very coarse language. So an atom sits in a solid. Nearby, it has other atoms similar to itself, periodically spaced around it. The atoms, if you remember, have electrons, and these electrons can actually see their closest electron. And if they want to, if the conditions are correct, they can actually start to align relative to their nearest electrons. This local alignment of electrons leads to phenomena such as magnetism. So your bar magnets or the magnets you have on your fridge, these are a consequence of electrons coupling to their nearest neighbors and forming some periodic arrangement between them. Now, in superconductivity, something weird and wonderful happens. Electrons can start to couple with other electrons that are really, really far away. So in magnets, the electrons have to couple spatially in geometry space. They have to see their nearest neighbor and couple with that, and that leads to magnetism. In superconductivity, you don't have to be your nearest neighbor. You can couple in energy space. So we can have these weird and wonderful things like quantum entanglement, where an electron can see another electron 100 nanometers away. This is an astronomical distance for an electron. It can see another electron 100 nanometers away in energy space, and through quantum interactions, these things can now couple. Now, there's all this weird and wonderful words like phonons and stuff, and it's a very deep, complex underlying mechanism that stabilizes these pairs, these Cooper pairs of electrons. But that's really the take-home message, where when I think about superconductivity, I always start off with magnetism. I think about how electrons see their nearest neighbors and start to arrange themselves, and that leads rise to the form of magnetism. But in superconductivity, this coupling no longer has to be in geometric space. it can be in energy space. And here we enter the weird and wonderful world of quantum mechanics, where things can now entangle over very, very large distances. And as a consequence, you can get weird and wonderful properties. Okay, so it turns out all metals should be superconductors. If you cool a metal low enough in temperature, so low that the electrons are now and the atoms are all slowing down, in essence, all metals should reach a quantum configuration where they can undergo a superconducting transition state. However, in reality, for many of the metals, we just haven't got low enough in temperature to observe this. So in terms of the metals in the periodic table, niobium has the highest TC temperature, the highest superconducting temperature of 9 Kelvin. This isn't so technologically useful for us, but in terms of the elements, it has the highest record. Second to that is technetium, and we have a successful technetium program here led by my postdoc, Dr. Emily Siska, and there we're very excited about the properties of technetium. But the elements themselves, although some of them, or most, in essence, all of them should superconduct if they're metallic, they generally have very low superconducting temperatures. So below this temperature, below 9 Kelvin, is when niobium becomes a superconductor. That's minus 260 degrees. It's completely technologically useless. However, as time has evolved, we as scientists have developed weird and fanciful, wonderful and powerful protocol to make compounds that have reasonably high superconducting transition temperatures. So here we're looking as a function of time since the discovery by owners in 1911 against the superconducting transition temperature. And so for the first 60 years, we only really measured the elements, and the superconducting transitions were very, very low, below 10 Kelvin. As our ability to make materials advanced and our understanding of the underlying principles also advanced with that, we could start making more and more complex materials. In the 80s, there was a revolution in the cuprates. This allowed us to reach reasonably high temperatures, so up to 160 degrees Kelvin, which is still pretty nippy. It's pretty cold. And that was really about it. And there was really a revolution in 2014. And this is where my story begins. In 2014, the work by Michael Eremut at the Mainz Max Planck Institute in Germany really led to a paradigm shift in how these materials were thought of. He took smelly hydrogen sulfide. So if you've been to Yellowstone National Park, you can take smelly hydrogen sulfide. He took it and he squeezed it under incredible pressures that are comparable to the center of planets. And I'll get to that in a minute. And what he found is he could take hydrogen sulfide and turn it into a very high temperature superconductor. So under extreme pressures, hydrogen sulfide becomes a 200 Kelvin superconductor. You know, that broke the record by about 50 Kelvin. And that was really remarkable. It meant that you could take materials that were really unexpected of them to do anything beyond smelling bad and so on, and manipulate these under extreme conditions and allow them to enter unique quantum states. And this is where our story begins. This, as a young scientist reading this, I wasn't that young in 2014, but reading this, it already allowed me and Ranga, who at the time were working for Isaac Silber at Harvard, we already started contemplating how we could take this remarkable piece of work and start playing with it and start pushing that temperature, that TC temperature, much higher by about 100 Kelvin towards room temperature. And so this is where my story begins in terms of what we as a group do. And we as a group, we study the materials, we study matter under extreme conditions. And when I mean extreme conditions, I mean pressures that are comparable to the center of planets and temperatures that are comparable to the surface of a star. Under these very extreme conditions, there's weird and wonderful science occurring already. Some of my favorite examples are if you take sodium metal and squeeze it hard enough, it actually becomes transparent. It becomes a non-metallic material. This photo here is light shining through the back end of a sample of sodium. So you're looking at it in terms of transmission geometry. And this is the light traveling through the sample, hitting your eye. So you can take metals and transform it into non-metals. You can take molecular species like carbon dioxide under extreme pressures. You can make CO2 into a glass. You can make it into a 3D polymer. So this ability to take pressure and manipulate matter was already known to be an incredibly powerful tool, but it hadn't really been applied to high temperature superconductors until 2014. And since 2014, there's only been one other study that really managed to utilize this technique. And so when I talk about pressure, we talk about extreme pressures. The pressures we need to manipulate matter in the way I'm talking about has to be high enough that you can start pushing atoms closer and closer together. And as a consequence, you can change the energy of the interaction of these atoms. So a common unit in our community is, we call it gigapascals. So 1 gigapascal is about 10,000 bar. In freedom units, there's some silly unit here, but the pressure in your car tire is about 2 bar. The pressures to make hydrogen sulfide become a high temperature superconductor is 1.6 million bar. And so these pressures seem incredibly high to us. Of course, as humans, they're incredibly high, but to Mother Nature herself, she does this readily. So the pressure in the center of the Earth is about 3.6 million atmosphere. The pressure in Jupiter is about 70 million atmosphere. And so Mother Nature readily plays with pressure and temperature incredibly well. We as scientists have tried to exploit this capability that she so cleverly portrays, and try to utilize it in the lab to make exotic states of matter. For that. Okay. So in our lab, we have a common piece of kit. This is called a diamond anvil cell. This is our bread and butter device. This utilizes 2 optically transparent diamonds. So these are diamonds that you would find in jewelry. And in fact, what we do is we take your diamond that you find in your ring, we turn it upside down, and we cut a very, very small area at the tip. And the reason for this is pressure is force over area. If we have a very, very small area, we can get very, very high pressures. And in fact, if the area is incredibly small, we can start getting pressures that exceed those at the center of planets. And so we have 2 gem quality diamonds. Our sample sits in the middle of these 2 diamonds. We have a metallic gasket that stops the sample from slipping outwards. And we press down on these 2 diamonds. This device is handheld. This is a very arty photo of it. So it can fit nicely in the palm of your hand. And in this little device, this can replicate the center of a planet in this little handheld device. We do it readily in our lab. What's also critical is that not only is diamond the hardest known material we have available to us, but it's also optically transparent. And as this photograph shows in our lab, we can shine lasers through the diamond, and the diamond allows us to have a portal into our reaction chamber. So it's just an incredibly powerful device. And in fact, I've started calling it basically a material search engine. Because we're able to manipulate pressure and in fact temperature using lasers so readily, we can scan very quickly for exploratory phase space. And as a consequence of that throughput, we're very able to readily find new materials of interest. So we have this handheld device. It can manipulate pressure as much as possible. And now what we can do is go back to our plot that I showed to you previously, which is the superconducting temperatures of the elements. And using pressure, we can do things like we can squeeze oxygen until it becomes a metal. So you can make oxygen into a metal. And then once it's a metal, it actually shows a superconducting transition at about 3 Kelvin. We can do it to sulfur. We can do it to nitrogen. We can, in fact, do it to hydrogen. And so now our superconducting transitions for our elements actually starts to get more complete, because using pressure, we can take materials that weren't initially metals and force them into metallic and superconducting states. So it's an incredibly powerful program to diversify the kind of materials we're interested in. Our story starts with metallic hydrogen. So hydrogen is a gas. If you cool it down to about 20 Kelvin, it becomes a liquid. If you cool it down below 13.8 Kelvin, it becomes a solid. But it becomes a transparent solid, just like a plastic. It's a transparent solid. Now, if you take that transparent solid and compress it incredibly hard, you start pushing the atoms closer and closer together, and the atoms start to share electron density, and you keep pushing them, you keep pushing them. Eventually, when you get to about 500 GPa, so nearly 2.5 times the pressure of the center of our Earth, hydrogen transforms into a metal. It's mind-blowing. It's one of the fundamental questions in physics, and we were very fortunate, Rango and I, to work on this problem under the supervision of Professor Silvera. What's important about metallic hydrogen is predicted to be a room temperature superconductor. So we were working on metallic hydrogen. We knew it was predicted to have these remarkable properties. We also knew that the pressures you had to get to were just so high that the kind of measurements we were interested in would be impossible. And so we were like, okay, so we know metallic hydrogen does this. We know hydrogen sulfide also shows remarkable properties. Can we find a way where we can merge these kind of ideas together and achieve room temperature superconductivity, but at a much more modest pressure? The way we thought about it is the following. Now, the diamond anvil cell allows you to squeeze materials. You can take something and squeeze it incredibly hard and change the free energy of the system. Now, what about keeping the box fixed? And instead of squeezing the box like before, making it smaller, we keep the box fixed, but now we start putting larger species into the box. So this is the train in Boston, the T in Boston. This is on a I don't know, Tuesday afternoon or something. It's pretty sparse, pretty unpopulated. So instead of reducing the volume of the cabin, what you can do is start stuffing people into it. Now, for you as a person, you can't tell the difference whether there's loads of people pushing onto you or the fact that your room has closed in on you if you were wearing blindfolds, for example. And so this idea that we started having was, can we start doping metallic hydrogen with larger atoms so that it could feel like it's under immense pressures, but actually we wouldn't have to go to these silly pressures to achieve the quantum states we're interested in. So this idea of chemical doping came to our minds. And in fact, this is a photo from Boston. This is No Pants Day. It's once a year where individuals decide to ride the T with no pants on. And the reason I like this photo is really what it is you can really pack that tram full of people, so much so that you start ripping electrons off or ripping pants off. So this analogy of not only are we able to reduce the volume of the box with a diamond anvil cell, but actually we can keep the box static and start putting larger atoms into the box to start implementing some kind of chemical pressure on the species. Now, obviously, one can do this. In reality, it doesn't always go to plan. A great example is India. I'm pretty sure they had some pretty strict SOPs on how to get people on a train. Obviously, in the lab, things can go absolutely crazy. The complete antithesis to India is Japan, where you have paid professionals that push people and pack people into an already pretty packed cabin. But jokes aside, this really is a very good pictorial way to think about what we're up to. We know metallic hydrogen should be a room temperature superconductor, but at incredibly high pressures. Can we dope metallic hydrogen in essence with larger atoms that allows us to relieve some of the pressures, the mechanical pressures we need to get to these quantum states? And in fact, yes, we can. That's exactly the mindset we approached entering this project. So we want to dope metallic hydrogen. We know it's a high temperature superconductor. We want to dope it. In fact, we even had a helping hand. It was even made easier for us. We knew hydrogen sulfide was already a high TC superconductor. So in fact, the name of the game was to find a sweet spot between hydrogen sulfide and hydrogen where we could dope the system in such a way to achieve RTSC, room temperature superconductivity. And the way we did this is we've actually did something very different to the rest of the community. Nearly all of the community has been working on combining hydrogen with some other elements. We decided to approach it using a ternary composition. So now we add 3 elements into the mix. We have hydrogen, which is the backbone, the mother matrix, and we actually add carbon and sulfur into the mix. And this very delicate incorporation of carbon and sulfur into the mix has allowed us to basically synthesize a material that has just the right amount of hydrogens to allow us to achieve this very, very high temperature quantum state. And so we've basically doped our metallic hydrogen with carbon and sulfur. And so before I go into the physics of it all, these experiments are incredibly complicated. Science is hard. Science is really, really hard. We have spent 5 years, both in our own laboratory and also at large-scale facilities, developing instrumentation that is going to allow us to understand on a fundamental level what is going on in these materials. We want to have an atomistic picture as these materials evolve and our understanding evolves with them. And so I just want to highlight that the hard work my group has done. And what I want to show you is the elegance of this material. So we have this material, we put carbon, sulfur, and hydrogen into a diamond anvil cell. So this is two diamonds opposing each other while our sample is stuck in the middle. Because the diamond is optically transparent, just like this photo is showing, we can shine light into our chamber. And actually for this material, we use light to transform the carbon, sulfur, and hydrogen into our magic material. So this is just a short demonstration. This is us looking through the top diamond into our sample chamber. This ring on the outside is that metallic ring that stops the sample from slipping outwards. And what you see with this powder here, this black soot, is actually carbon and sulfur. So an elemental mixture of carbon and sulfur. And this clear material here is hydrogen. And we're able to shine green light onto our material and initiate a photocatalytic reaction. So we can put our materials into this magic, well, it's not magic, into this handheld device, and using just green light, we can initiate a photochemical reaction. And as you can see, the black soot is disappearing, and in its place, what appears is these transparent crystals. I'm just going to quickly fast forward. And as we walk the laser around, we can initiate this reaction. What's actually occurring on a deeper level is that we're forming the S8 polymers undergoing a radical reaction, which in turn sets off a chain reaction, which leads to the formation of hydrogen sulfide, methane, and hydrogen. And we end up making a Van der Waals crystal. That was a lot of chemical chat there. But what's important here is we can put these three elements together, shine green light, and we can get out this beautiful crystal. And this is it. This is the magic stuff. This material, I'm going to demonstrate, if you take it and squeeze it and measure its properties, is the first demonstration of superconductivity at room temperature. So again, things are very complicated. Professor Rangadias at University of Rochester has spent many years developing the protocol we need to do these measurements. This is, for your attention, this is a 30 micron surface where we've spotted leads onto the center of this material, onto the center of this diamond, and our samples sit in the middle of this. So these are some of the hardest measurements you could do in experimental science. It's really taken 100 years of standing on the shoulder of giants to be able to pull off these measurements. And so here we are. So I'm going to talk you through some of the good stuff. It's going to be a 2-hour talk, Corey. This is just like Onus's picture at the beginning. At the bottom, I have temperature, and on the side here, on my y-axis, I have resistance. So what happens if we follow just the blue curve here? You cool the material down, and as the atoms slow down in the metal, the resistance is lowered. The electrons can flow more easily from A to B. At some critical temperature, there is a sharp, dramatic downturn to zero resistance. This is indicative of a superconducting transition. One of the hallmark properties of superconductivity is zero resistance to electrical flow. What's important here is as we compress the material, as we squeeze on it harder, and we remeasure this property, the superconducting transition temperature increases. This is a very important observation for us. So you take this material, it's superconducting, and as you squeeze it, its superconducting transition temperature increases. And in fact, what we find is these values represent pressure. As you increase the pressure, the superconducting transition goes to higher and higher temperature. So these plots move further and further to the right in terms of temperature. Now, in addition to zero electrical resistance, the real signature for a superconductor is something called the Meissner effect. Superconductors repel magnetic fields. In fact, superconductivity and magnetism hate each other. As you pass a magnetic field across the superconductor, it uniformly dispels all of the field. Because of this property, or this characteristic of this material, we can do something called AC magnetic susceptibility, where we can show the diamagnetic response of the material. These are big fighting words for the general audience. But what's critical here is we're the only groups that are able, in partnership with Ranga Dias group, we're the only people that can pull off these measurements. These are super complicated measurements. The samples are incredibly small, and what we're trying to measure is incredibly subtle. But we can see the shielding response of our superconducting state due to the Meissner effect. Also, what's important is, just again for my few fellow physicists, these Cooper pairs, these electrons that are entangled in energy space to each other, actually have opposite momentum vectors, whatever that might mean. And what we're able to do is we can apply a magnetic field, and the magnetic field generates a force between these two electrons that breaks the superconducting state. And so as you increase the magnetic field, you can disrupt the superconducting state, and you can lower the superconducting transition. And that's exactly what we're able to demonstrate. The pink or purple is where there is no applied field. So this is the clean superconducting transition with resistance as a function of temperature. And as we increase the magnetic field on the material, this breaks the Cooper pairs, and the superconducting transition temperature gets lower and lower and lower and lower. This is the crowning piece of work. This is what got us all the attention. This is truly indicative of a superconducting transition. This response to magnetism is the true hallmark of this quantum phenomena. So, bunch of complicated stuff, did a bunch of science. What we're able to show is that this material, this carbon, hydrogen, sulfur mixture that we can put into a diamond amber cell using green light, photocatallically convert into this magic crystal of ours. Then when we squeeze this material, it undergoes a transition eventually into a superconducting transition, which with pressure, its superconducting temperature increases. And so as we increase pressure, the superconducting transition increases. It actually reaches a critical pressure, which is very high, but that's irrelevant. And its TC just shoots up. And it's at this higher points here that we achieve room temperature in this material. So we're able to measure superconductivity at room temperature. And I really want to clearly state here, until about the 1970s, it was assumed you could only have superconductivity occur at ultra low temperatures. There was really a paradigm shift in the late 60s and early 70s that really made us rethink about coupling phenomena within these quantum states. And so this is the evolution of our material. This is all very exciting. We've been able to add a dot to this map here. More importantly, we also are about to publish our second work, where we have the second highest TC temperature of any material. And the idea is to really monopolize these materials over the next coming months. But so what? So you have these materials that occur at very, very high pressures, and they do show superconductivity. But why is superconductivity even important? Well, currently, the use of superconducting materials in technology is very, very limited. And the reason it's limited is because, just like I showed you for the plot of the elements, you have to go to very, very low temperatures to achieve these superconducting states. And as a consequence, it's very, very expensive to run these instruments. And so the main two instruments that are used in today's society are MRI machines for medical imaging scanning, and a SQUID, a superconducting quantum interference device. Now, we obviously all want SQUIDs in our homes, and we're working very hard to get everyone a SQUID, but the use of the superconducting materials is very, very limited, and it's very bespoke and generally tailored either for medicine or very esoteric physics measurements. But what if we can actually lower the pressure in these materials? What if we can start lowering the pressure in these materials, which we're very confident we can do, and retain the room temperature superconducting properties. Now, if we're able to completely release the pressure, and our aims are to do that within the next 5 years, then we can completely transform the way technology is utilized and used in today's society. I just want to, my last 10 minutes, Corey, I just want to show you a video of some of the remarkable properties of a superconducting material. Now, this is obviously at low temperature because the puck you'll see is cold, but enjoy the video. Amazing music.
So what if we got here? So we have quantum locking. The superconductor is locked in space, and it stays wherever I put it. You see, this is quantum trapping.
It's amazing.
As long as it's
so the
cold,
it's superconducting. It's frozen with liquid nitrogen.
Upside down.
Right.
And it stays locked.
So the fact that it's superconducting is locking the magnetic field in 3 dimensions, right?
Yeah, exactly.
And that
and
pivots.
You see, because this is symmetric, it can rotate without break the locking. The locking doesn't break.
Right.
Because
it stays there on the X and Y, but not on, it pivots on the
on the axis of the magnets. You see, if I can move it on the side, it will again pivot around the axis of the magnet, because it makes sure that the magnetic field inside of it stays the same.
Right. It's astonishing. Can you put it on the track for us?
Yeah. I just levitate it above the track quite high, and I can just rotate it.
So it's actually floating above the surface.
Yeah, it's not floating; it's locked above the surface.
So you could tilt it at an angle, and it would still fly around
like this, and it will just go around like this. Because I go and put it at different height, and then like this.
And lock it at the height.
Lock it, different height, different configuration.
Right.
And I can even lock it opposite way. If you could just hold for a minute.
Okay.
High. I'm doing the same thing. I'm
locking
it upside down, and then it is suspended.
Fantastic. Okay.
Pretty amazing. And I was just talking about the music. So that puck had obviously been immersed in liquid nitrogen. It was incredibly cold, and it had to remain cold for it to be able to remain in a superconducting state. But the fact that we've been able to realize superconductivity at room temperature, and our plans of utilizing this chemical pressure technique of lowering the pressure significantly, could allow you to start fantasizing about a society where we have room temperature superconductivity readily available to us in all types of materials. And what that really allows you to do is finally fulfill the predictions of Back to the Future 2 with hoverboards. The realization of maglev trains could easily be a reality with this kind of technology. What I find more instrumental is the onset under the complexities revolved in climate change. Now, the energy grid is really one of the most remarkable engineering innovations of the 20th century. But currently, as this map shows its spread, there is about a 5 to 8% loss within the grid system in the US annually. This equates to about $30 billion a year loss in energy, just in the US alone. That number is close to $1 trillion globally. And this is a consequence of that resistance in all metals. So the grid is actually made up of aluminium because copper is too expensive. And all metals have an inherent resistance, and you just can't overcome this. And as a consequence, we have a $30 billion a year loss here in the United States alone. Furthermore, the amount of energy we can transport across the grid is limited. Our society's demands are forever growing, and we really have to think about a more viable, greener solution. Now, one could envision that once we reach a technology-based solution where we can print materials like room temperature superconductors, then a complete revolution and transformation of the energy grid is totally viable. And again, what's important for us here in Nevada is that we have some of the most number of photons anywhere in the world. You could envision very easily that with a superconducting energy grid, somewhere like the Southwest could become a solar hub, right? You become an energy farm, you set up all the solar farms, and from here we can then distribute energy without any loss nationally, if not globally. And so with that, really, I'd like you to just take into account all the exciting and new things we're doing here at UNLV. And one of our real highlights is we want to take you into the superconducting century. And I leave you with the front cover of Time magazine, which was from 1987. I think they've waited a long time, but I think we're really there as a society. So anyway, thank you so much for your time, and I hope you enjoyed my talk.
Thanks so much, Ash. That was great. Really appreciated it. If you have any questions, we'll give everyone a couple minutes to put some in the chat. Looks like there's one here. Have you had any opportunity to collaborate on this work with other UNLV professors or research labs at the university?
Yes, so we are currentently working towards building a focus group working on just these materials itself, and we've already submitted several NSF EPSCoR grants. But yes, of course, we're very fortunate to have a critical mass of experts in this field to run with this.
Awesome. Any other questions? Put those in the chat. I thought it was it helped me. I don't know anything about superconductivity, so that actually helped give me a really good background and explainer. So thank you so much for that. I don't see any other questions.
I'm going to call people out, and I want them to solve the Schrodinger equation for a equally charged superfluid.
Who do you want to call out?
Okay, no one.
So Elizabeth asked what school you work at now, which is UNLV, but if you want to answer that, you can too.
Yeah.
Oh, she said it was a joke. Okay.
Okay. No, so I'm okay with no questions. So generally, I really hope that...
oh, I got it, Elizabeth. Sorry.
It was pretty funny, Elizabeth. I really hope that you can take away from this just the excellent work being done here at UNLV, and the fact that this kind of discovery and this kind of high-end science, we're at the forefront of it. No other groups are really at the stage at which we're at, and I think it's a very exciting time for the College of Sciences and for UNLV, as well as for my own group.
And Elizabeth did have an actual question, which you kind of answered there, but she said, what do you expect to do next with this?
I think Eric Chronister, the dean, is buying me a Lamborghini as a thank you for all my hard work.
Well deserved.
Thank you. The emphasis is to lower the pressure dramatically. So the end goal is to actually eliminate the need for pressure. So all pressure does is change the interatomic distances between atoms. You can do that without pressure. The trick is how you do it.
Great. Awesome. Well, thank you everyone so much. Thank you again, Ash. Great presentation. And as I said, it will be available on the website within the next week. So if you want to come back and watch it, maybe you missed something, feel free to check it out. And thank you all so much. I hope you have a great Thanksgiving, and hopefully you get some rest this weekend.
Thanks, everyone.
Take care.
Bye, Mom.
Oh, Eric asked a question.